there is this. Okay, so we're gonna start the next talk of this morning session. It is my pleasure to introduce my good friend John Fricks. We know each other for over, I don't know, 12, 15 years or something like that. And we see each other in conferences and so on. So today it's my pleasure to introduce, to chair the session. John Fricks currently at Arizona State University, previously at Penn State University. And today John is going to have a renewal-reward process arising from solution diffusion systems with application to cellular transport.
Okay, thanks. This is a project that we always think to be about 3 days from submitting. For a year or so. Veronica was a recent graduate from Brown Applied Math, and she saw some papers I did in the early 2010s about renewal-reward processes in motor transport. And she had been doing working on a different transport system, and of course coming at it from an applied math perspective, and trying to make sense of what she was doing with what we had done. And so this project has been us trying to make those two things talk together. So it is with Peter Kramer and Scott McKinley, and Veronica's on the job market too. But yeah, Pete and Scott are on a project with me, with Will Hancock, who's an experimental collaborator working on motors. I'm going to talk a little bit about that research because the examples play in. Okay, so just to talk a little bit about cell transport. This is a typical biological model, a cartoon that's not very proportional. Right? So this is a neuron, or a cartoon of a neuron. And these can be up to 1 meter in length. The neurons that grow down your spine are quite long. So you need to get material from the cell body near the nucleus out to the other parts of the cell. So along the axon, out to the synapse, you need to get different materials to different locations. Right? And so there are some things known about it, but there's a lot of mystery about how that is controlled. How do you get different cargoes to different locations? And a lot of the focus on cell transport has been the efficiency of cell transport. How quickly can you move things from here to there? But I always, when I see experiments and theoretical papers that focus on that, I always come back to that's not what you're trying to do. You're not trying to get things as quickly as they can be. And that certainly plays a role. You want to get them to where they're supposed to be, right? That's a slightly different question. Okay. Yeah, so these are microtubules that go out along the axon, and they have a polarity. There's a negative end and a plus end. And then molecular motors. So this is a real cartoon of kinesin. I'll show you the structure in just a minute. And they tend to move to the plus end. And there's dynein, which are represented by this guy. They tend to move to the minus end. And by tend to, I mean kinesin takes roughly 100 forward steps towards the plus end with 1 minus step. So it's one small for the plus end. Okay, so just in a little more detail, the microtubule is made up of these tubulin units, and they're 8.2 nanometers each. And the kinesin and the dynein, well, especially the kinesin takes exactly 1 step, and usually in the plus direction, and the dynein in the negative direction. And there's another molecular motor. This is myosin. And myosin is the motor that moves actin and elongates muscle cells. So it was the first one discovered.
And this is the scale, so dynein is slightly smaller than kinesin.
Yes, these are the left. And myosin can take much longer steps. That has this where the kinesin is actually quite constrained. It pretty much will never take another step. It has a hard time taking a side step where it moves tracks in the microtubule. It can do that, but very rarely. Under certain conditions. Okay. Here's here's a movie of how things work. And one of the important things is that it has to go through this chemical cycle in order to step. And this is a simplified version of the chemical cycle. There's probably more things going on than that. I used to show a very complicated one just to show how, like, what some people hypothesize, how complicated it can be. But also notice that the heads have to actually physically move forward. And also notice these are each about 5 nanometers in diameter, and so it absolutely doesn't look like this in the cell. Right? It's not bouncing around, and there's no Brownian motion, right? It's taking nice, consistent steps, and that's not really how things work. So how I got into these renewal-reward representations, which I'm going to tell you about in just a minute, is that we were trying to model the diffusion in addition to the kinetics, because we were looking at neck linker extensions. So the diffusion, the constrained diffusion, was being modified. So we had this sort of SDE mixed with kinetics model. But the heads are switching which one is actually moving. So it's kind of weird to write down the model. So what we try to do is make a very local model that we're going to put into a larger stepping model. Okay, so this is like the idealized. There's all this stuff going on between here and one of these steps, right? There's the kinetics, there's the diffusion. So the rear head usually detaches. So this is usually what happens. This can occasionally happen, especially if the motor is under force. And then it could just step back down again, which means you make no net movement. It could move forward, like here, and you get a net 1, similar thing, and a minus 1. Again, this is pretty rare in kinesium, but it can happen. These might be more rare. It's hard to observe. Okay, so we could think of this. So here's
Sorry, John. So there's a rotation involved.
There's a 3-dimensional.
And so is that randomized in the sense that if it continued in the same direction, you'd just twist?
Right. It's pretty. The neck linker is pretty constrained, so there's not a lot of. But when you're, the idea is that the ATP docks the neck linker, so that when ATP binds, you get a forward bias. This is what you're asking.
No, it was the angle of the rotation. So if it continues doing this every time,
Yes.
it's going to twist itself around, isn't it?
Right.
So I was wondering if the rotation could be either way,
Yeah.
in order not to impose a direction on the twisting.
Yes. Then that's what happens.
That's what happens. So it could go either way.
Yes. Okay. Right. So how do we represent the stepping? So this is a renewal process. It looks kind of funny, but all it means is this: you take a random amount of time and you step, and then you take another random amount of time, and those random times are identically distributed and independent of one another. That's a renewal process. Poisson is the simplest example, right? Where those times are exponentially distributed. And then you have these rewards, and your reward is that you get to step. Okay. So those could be independent of these times, but they don't need to be. So this is a renewal process. He's going back to the 50s. So there's a lot of work, and it's really classical. But what we had was a complicated model, and we needed to calculate the moments of these guys to be able to say what this process would look like. I don't have that. Yeah. So I'm going to come back to that. Okay. But that's what a renewal-reward process is. And so you can use it to represent those steps. Okay. In the cell, there's not one motor attached to one cargo. There's a lot of experimental data that is precisely that. So we have a lot of data about single motors, single kinesin, and single myosin. You can isolate the kinesin, you can attach a latex bead, and you can either put some kind of fluorophore or Q dot, or you can use a laser trap. And you can manipulate these motors and get lots of cool data out of it. The question is, how do these work together in the cell? So each one of these cargoes has multiple kinesin and multiple dynein. And of course, you can replicate that on a slide, but it's really hard to take that single motor data and put kinesin and dynein together in a model and then replicate that behavior of a cargo with lots of motors.
So the same cargo could have motors that are trying to go in opposite directions.
Exactly the craziness, yes. That's right. It's like having a car with two motors that are both on in opposite directions. So I mean, that almost certainly has, well, that could be modified so some of them aren't operational, right? Let's get to that. Yes, but that's one of the big questions. Because again, you're trying to get the stuff where it needs to go, and sometimes things need to go back to the body. So those dining are helpful, but they can also modulate the kinesis behavior.
But presumably the vesicles have to be coded for where they're going. If they are coded, does that not determine which motors would attach to them?
That's one possibility. And there are also modifications of the microtubules themselves that change the stepping dynamics.
So some tracks may be used preferentially in one direction rather than another.
That's a possibility. Yeah, there's a lot of unknowns, and to add to all of the unknowns, the microtubules are undergoing their own dynamics of being created and destroyed. Okay, so there was a model that I'm going to show you in just a bit more specifically that was Klump and Lupowski, the tug of war model that got a lot of traction, and it was somewhat predictive. Well, people could try to understand their experiments with this. It's basically a simple force balance. So you count how many kinesin you have, you count how many dynein you have, and you add up their velocities through a nonlinear function, and that's how fast you're going. That's it. So it's a simple Markov switch that tells you how many motors are attached, and then you add up the forces and decide how fast you're going. So it's the nice thing is it's easy to understand. Okay. So so here's the interesting thing about the coding business. So our experimental collaborator, Will Hancock, wrote this review paper, The Paradox of Codependence Among Antagonistic Motors. Because there's some in-cell evidence. He does mostly experiments on slides to isolate all the motors to try to experiments. But there's some in-cell evidence that if you take the kinesin, you take motor cargo complex. So you have kinesin moving to the plus end, and dynein moving to the negative, and you knock out the dynein function. You'd think what would happen?
Going the other direction.
It would go the other direction. And it doesn't. It actually goes slower than just a kinesin by itself. And you can reverse that phenomenon too. You knock out the kinesin and you think it's going to go to the negative end, and it doesn't. So somehow these motors are interacting with each other to activate each other, they're chemically interacting. So we have a couple of broad hypotheses about how this works that we're slowly trying to test using something called the DNA origami, which I'll show you in just a minute. That maybe the dynein helps you stay attached, right? So knocking out their function, you lose that, and so it's not that they're going slower, it's that they're becoming detached more quickly. So you're just not seeing the movement. Mechanical activation is a more interactive phenomena where being pulled back actually sort of turns your motor on. And the steric disinhibition is a hypothesis about chemical interactions, and that could be happening through an intermediary. There could be some protein that's causing them to interact. And there's lots of proteins associated with dynein. So dynein is rarely seen in isolation. So what Will got working in his lab is called the DNA origami. He didn't invent these because these are floating around. You create DNA structures. The nice thing about them is you can have these binding sites for the tails of motors that are specified for the type of motor. So you can, like I mentioned, it's difficult to do experiments because if you just throw beads in with lots of motors, you just have no idea how many are attached. But this way, what you can do is, for example, limit yourself to 2 kinesin motors only, or 1 kinesin, 1 dynein, 2 and 2. So that's we're trying to work up to 2 and 2. I'm not talking about the data analysis today because it's really hard. It's hard to figure out what's going on. So we're still working. But this is our motivation for going back and trying to understand these multi-motor systems. Okay, so this is how a lot of applied mathematicians have written down these switching diffusion systems. Okay, so you have this is a kinetic, transition matrix. We have velocities, and we have diffusion, and you can assume that the kinetics are really fast, and you can reduce down to a single system, right, where you have an effective velocity and effective diffusion. Or you can do homogenization or averaging, where you have large spatial areas. So this is the framework that Veronica was first looking at things. So we want to see if we can get effective diffusion and velocity. Just looking at the a more random variable, working directly with the variables. So this is a way that you could write this down in terms of an SDE. I've not written the associated Markov chain. You have a continuous time Markov chain with constant rates, and that's J of t. Okay, and these are the jump times. All right, and JK is the state at the kth switch. Okay, then you could have an SDE that might include the last switch time, the location of the process at the last switch time, and you may or may not have a fluctuating term. So this might also go away, and I'll show you examples where you just have a straight velocity, so it'll just be a solution to it. Okay, but so this is what we have in mind. I guess it's important for me to point out now. The way we're gonna look at this is through regenerative processes. So we have this Markov chain, okay, and we have n+1 states. So the 0 state is going to be special. We are going to, whenever we get back to the 0 state, we're going to sort of start over. Okay, and so this is going to break time into independent times. The amount of time to leave state 0 and make it back to state 0. Okay? So what we're going to do is we're going to look at the reward that we get these independent times. And that's going to be the total displacement that happens as you move through the states. So you start at 0, when do you make it back to? So these are the T1s. These are the regenerative times. And between here and here, you have to move through the Markov chain. And when you're in these different states, you're going to have different modes of moving, right? So move to the plus end, move to the minus end. Sometimes the motors go into weak binding. But we're actually thinking of even broader transport systems or biological systems that involve diffusing and binding, which there's a lot of. You may have movement without any variation, or with so little that it doesn't matter. Okay, so you can include all of those in the system. But if you have a 0 state, it's when you get back to the 0 state, you start over. So our times are going to be independent and identically distributed with the possible exception of the first time. But that won't matter as we talk about it.
So John, sorry, just a quick question about the states. So is this, I'm imagining, in the simplest possible scenario, 0, 1 would represent on and off, but now you're kind of allowing for more.
Yeah. So one thing you can think of with even just the 2 motor system where you have kinesin and dynein, maybe it's simple enough, but maybe it's simple enough that you could just have the kinesin is attached and the dynein is not. The dynein is attached, or they're both attached and they like stop or move slower. So now you have these sort of 3 states of motion. Yeah. But you could have 4. Now how many do you have? Right? So, any questions on the basic idea? So I'm going to just run through a couple of examples and then hand wave through what we did because the calculations are just really messy. But the idea is relatively straightforward and really just putting together some tools from classical applied probability. So this was the kind of system that Veronica was looking at in her dissertation. And this is just plus and minus, and you could have some kind of effective diffusion, and then stopped. So this could be like both motors attached, dining, kinesin, and then maybe there's some kind of weak binding state where you're effectively diffusing. And you can see that with some motors, which could be an interesting part of the whole multimotors.
Sorry, can you explain those equations? What they?
Oh, sorry. Yeah. So, yeah, good. These are going to be the rewards in different states. You're right. So we're going to have these. So you're in state 0, okay, and that's going to be the diffusive state. So since you have this Markov chain controlling time, you're going to wait an exponential amount of time, and that rate, and that's going to be this. And it has a 0 because that exponential time depends on the fact that you're in state 0, right? So then you have diffusion, and then this is a standard normal, right? So that would be how far you travel while you're in state 0. This would be that random time that you're in state 1, which is a sort of positive velocity. But v is not random, it's just a velocity times time. Okay, so you're doing this. You start in state 0, you're going along, and now you move into state 1, and you're like this. Okay? I'm not arguing it's a great model. You know, like sometimes the motors almost look like that. It's really ridiculously strong. And then let's say you went to the 3rd state, and that's frozen. And then you went to state 2. And then you go back to state. So now we've completed an epoch. We started in 0, and we're now back to 0. Okay, and we're starting the Markov chain over again. And we'll have another setup. It could go through the states in a different order. That's right. Sorry. Yes. Yeah.
I mean, the way you've drawn it, ZK is positive. Would ZK necessarily be positive, or is there a strong positive drift someplace in ZK?
ZK could be negative.
Yeah, but then you would move to the left.
So these are the rewards. So they're the displacements. And
Okay.
Taus are the times, which is why no one understands.
Time is going to the right.
So times are exponential, so it's going to the right. But because it's Brownian motion,
Okay,
it's scaled by it.
okay. I thought that was your
Yeah.
track there.
Yeah.
Okay.
Yeah, and this is time, and this is the track. Yes, but you can't go backwards on the track. That's right. Okay, that makes sense. Yeah. So, yeah. Of course, you know, Veronica was just getting out, starting her postdoc at NDI. Of course, she's done all the work. And Pete, Scott, and I have just argued over notation for like, yeah. So this is another example. This is a cooperative model of transport. So Klump and Lepowski, before they did that, the model of tug of war, did a cooperative model. So this is, you should think of as just all kinesin. Okay? So you're going to have a velocity that depends on the number of motors. This could be an applied force. I told you could put a laser trap on the cargo. So this could be an applied force. This is a stall force. This is going to be the rate for the next detachment. So you have a rate epsilon for a single motor to detach. This is like a factor to take into account the external force. And then you have n for the number of motors that are attached. Right? And then this is for reattachment. So pi is the probability for reattachment. And I haven't, yeah, this should have been the last slide. But the tau k's are our times until the next event occurs. And that's going to be the sum of these two things. Right? And you're going to move up or down. And this guy is going to be your reward. And it's going to be the velocity times time. So this is just basically like, in our notation, how you write down the clump of Minkowski. Wow, 5 minutes. Okay. Yeah. And so this is a similar tug of war model, but I'm running close on time, so I think we don't need this because it's similarly argued. Okay. So this has two aspects. There's the what we call one of these a cycle. Okay, where you go through, you start at state 0 and come back to 0. It's a regenerative cycle. So we need to be able to do two things. We need to calculate. Well, this just came back to 0. We need to be able to calculate the statistics for this, which means the displacement and the time moments, the first moment and the second moment and the cross moment. Because if we can do that, then this is going to be like viewed on these chunks. It's going to be like a renewal-reward process. Okay, you need to be able to calculate all of the moments, and then you can find a functional central limit theorem, and then you can read off the velocities and the effective diffusions if you can do that. Okay. The problem is it's all you have to then figure out what's going on within a cycle. Can we calculate the total displacement and the total time within a cycle as you move through this Markov chain? And this is some of the classical stuff. There's the answer. So if you have the model for each of these times, you can do this, and I'm going to kind of boil it down this way. It's a one-step calculation. So you do the calculation of coming out of 0, and then these are just sort of iterative until you come back out of the model, right? Picking up the expected time and the expected displacement each step. But you can do them, it's basically like a geometric, but in a matrix way. So you can calculate what those expected times are. Yeah. So we did comparisons with simulations, with renewal-reward analysis, and with PDEs, and with, except for a few exceptions. And by the way, this kind of doesn't make sense in that this was from Veronica's project, and these are changing lots of parameters at once. So she just indexed those changes. But the more important part is over a large change in parameters, we got really good agreement. And this is just to give you an idea of what you can do when you've built all this machinery, is you can, for example, add loads to different numbers of motors. So these are cooperative motors. And with different responses of velocity to force. So you could have a linear response to force. You could have a sort of superlinear response and a sub response. So this is a sub, and this is super responsive. And so the dotted curves and the solid curves are the same, except the solid curves are linear. Okay. The point is you can explore a lot of different models without having to do all of the detailed simulations. And the advantage of putting things like this is all we need to do is calculate moments. So even if part of our step is like, I need to solve a nonlinear SDE, well, I could focus my simulation only on that, get the moments that I need, and then put it into the larger framework, right? You also don't need exponential times within a cycle. So you need that Markov chain structure, but the times that you're in a state could be something other than exponential. So that's the advantage of looking at it this way. I think I'm just going to skip through these. And yeah, here what we did is we, when you have one motor attached, it's easier to attach other motors. And so that's another thing that we can explore about modifying the transition rates. But I think I'm out of time, so I'm going to stop there.
We have time for questions. Yes, Ruth?
You mentioned that the microtubules are growing and shrinking and so forth. That was in Joe Howard's talk too. Have you incorporated that at all?
So they are not doing that in the experiments.
I see. Okay.
Because the experiments are you put the microtubules down and you stabilize them.
I see.
But it's a really interesting question more broadly of how in vitro experiments translate to, right? So if you're seeing something different in the in vivo, this is one of the many things that can be different. And what we're trying to do is slowly add elements of in vivo to see if we can understand that. But it's a very interesting question.
John, is there any quantitative evidence from in vivo studies as to the accuracy of the sorting?
The accuracy of the sorting.
Meaning, do the right vesicles get to the right place?
Oh, that's a good question.
I mean, I'm just wondering if we know roughly how good it is. Or is that very hard to measure?
You'd have to almost start with the presumption that if the cell was healthy.
Yeah, but there's got to be, but it's never perfect, right?
Yeah.
I mean, it's not.
But it'd be, I guess the question would be like, are you expending too much energy to do that?
Well, that
Yeah.
becomes the other question.
Yeah, because putting motors that go in opposite directions.
It doesn't. I mean, it's like all biology, right? You wouldn't design it this way if you were starting from scratch, but so.
Yeah. So I'm not sure.
Super naive question, but I guess in practice you would need to move motors to the different locations in order to have a motor there to get you back.
Right.
So you would also need to transport the motor.
Presumably they transport themselves, right? In that when the vesicle gets where it needs, when the ion channel gets to where it is needed, the motors will detach. There might be a slow process.
Exactly. But then they're in the wrong place, or
yeah.
And would need to be transported back to the start.
Yes.
Okay, cool.
Well, or you just make new ones.
So you would degrade them instead?
Well, they degrade it at a non-trivial clip. So, yeah.
So is the point of these models to be fit to data, or
I would say it's more to generate hypotheses, to make predictions. That's right. I would be. Well, you could to a degree. I mean, one of the problems with the is, I mean, it's great that we have time series now, and the problem is we have time series now. There's lots of things going on in the experiments, and trying to distinguish that from the biology is really tricky, and how to tie it to the model has been the challenge. So a lot of what has been done in the past is, how does velocity scale if we make this perturbation, right? And the sort of model, we can try lots of different models fairly quickly, so we have this sort of framework, we can take out this part and plug in something else. And so in that way, to understand experiments.
About some experimental observations that the kinesing step size is about 8 nanometers.
Mm-hmm.
So can it also take into account in your model about the discreteness in the moving?
Different lengths.
Yeah.
Or the 8 nanometers.
Yeah, for the move step size for
Yeah.
the kinesing.
When I said plus or minus 1, 1 is in units of 8.2 nanometers. No, you can definitely take that into account. That's not a difficult thing to take into account. And in a slightly different framework, we actually allowed for multiple steps of because I was studying the heads, not the multi-motor system. So we allowed for multiple steps. So you could go 2 tubulin array, and the wild type never does that, but these perturbed proteins can. And you can put that into a similar framework where you actually need a semi-Markov process, but it's very similar. And because it's a very simple structure for the underlying Markov chain, you can do a lot of the same calculations. You do it piecemeal. You have a big matrix, but you can do like one matrix at a time, which is much easier.
Okay, if no further questions, let's thank John.